Weisenfeld Tech presents RF Metrics Explained. This mini-course provides a high-level, practical introduction to key RF metrics used in cellular networks. Instead of focusing on complex theory, it emphasizes intuitive, hands-on understanding, helping technicians and engineers quickly grasp what the metrics mean and how they affect real network performance. RF metrics and measurements are essential for understanding how wireless networks perform in real-world conditions. Radio signals are constantly affected by their environment, including obstacles, interference, and user density. Engineers therefore rely on measurable indicators that describe not only signal strength, but also signal quality and interference. Metrics such as RSRP, RSSI, SINR, and PIM translate radio behavior into meaningful data and help identify issues like weak coverage, interference, or hardware problems. Together with adaptive modulation, these factors determine overall network performance, making it important to understand all aspects, not just signal strength alone. In wireless networks, including 4G, 5G, and Wi-Fi, the end-to-end quality of service depends on more than signal strength. A metric is a measurable parameter used to evaluate network performance. In this context, a device may show strong signal levels while still experiencing low throughput, high latency, or dropped connections because performance is influenced by multiple RF conditions. In cellular systems, RSRP and RSRQ provide additional insight into signal quality and load, while in Wi-Fi, factors such as RSSI, channel utilization, and retransmissions also reflect network conditions. Metrics such as RSSI indicate received power, while signal-to-noise ratio and signal-to-interference plus noise ratio describe how clearly the signal stands out from noise and interference. Power control, interference, overlapping channels, and external RF sources, together with background noise, directly affects reliability. Understanding how these metrics interact is essential for assessing coverage and maintaining stable wireless quality of service. RSSI in GSM, for LTE, 5G NR, and Wi-Fi. RSSI, or Received Signal Strength Indicator, is a measurement of how much radio signal power a device is receiving at a given moment. From a physical perspective, RSSI reflects the overall power of the received wave, which is directly related to its amplitude. However, RSSI does not measure only the useful signal from the serving transmitter. It measures the total received energy within a specific frequency band or channel, including signal, interference, and noise. A high RSSI value generally means that strong signal energy is present, high amplitude, but it does not automatically mean the connection will perform well. A device can show a strong signal while still experiencing poor data speeds if interference or noise is also high. RSSI in cellular networks. 2G or GSM, RSSI also called RX-LEV represents the total received power within the GSM carrier channel. In 2G, it gives a fairly direct indication of coverage strength. For LTE, RSSI measures the total received power across the configured channel bandwidth. Because LTE uses full-frequency reuse, interference from nearby cells can be high. Therefore, RSSI is not a reliable indicator of signal strength in LTE. RSRP is the preferred metric. 5G NR, RSSI reflects total received power and is influenced by beamforming, which can cause signal levels to vary. It is not used as the primary signal strength metric in 5G. Instead, SSRSRP is used to evaluate coverage. Wi-Fi, RSSI indicates the amplitude and total power of the received signal within the active channel, e.g., 20 or 40 MHz. It includes both the useful signal and any interference on that channel. RSRP in 4G LTE and 5G NR networks. In both 4G LTE and 5G NR, RSRP and SSRSRP is used within RRC to classify signal conditions and guide network behavior. It is mapped to predefined thresholds that control cell selection, reselection, and handover decisions. Stronger signal levels support more stable connections, while weaker levels may trigger mobility actions or impact performance. There is no formal definition of what constitutes good or poor RSRP, but according to 3GPP, these thresholds are widely used as a de facto standard. The diagram below illustrates for GLTE and 5G NR/RSRP levels, providing an approximate view of signal strength classification. Quality-related signal metrics describe how clean and usable a radio signal is, not just how strong it is. While signal strength metrics show whether coverage is available, quality metrics determine how efficiently and reliably data can be transmitted. Metrics such as SINR, RSRQ, RxQoL, and senior assess the relationship between the desired signal and unwanted disturbances such as interference and noise. When interference or noise distorts the signal, the receiver has greater difficulty correctly decoding the transmitted data. In other words, quality-related metrics indicate how clear the signal is. Strong signal strength alone does not guarantee good performance. It is the balance between signal, interference, and noise that ultimately determines throughput, reliability, and overall user experience. Signal quality in GSM, for GLTE, 5G NR, and Wi-Fi. In summary, the different quality parameters are intended for different network types. 2G or GSM, RxQoL, reflects the bit error rate and indicates how clean or disturbed the signal is. For GLTE, signal quality is evaluated using RSRQ, which reflects interference and cell load. Another key metric is SINR, which indicates how strong the useful signal is compared to interference and noise. SINR is directly related to achievable data speeds. 5G NR, signal quality is described using RSSRQ reflects how much interference or network activity is affecting the signal, while the SSSINR measures how strong the useful 5G signal is compared to interference and background noise. Wi-Fi, senior, signal-to-noise ratio, describes how strong the signal is compared to background noise and directly influences data rate selection and stability. In an RF environment, noise refers to unwanted random signals that exist within the same frequency range as the desired radio signal. Noise is always present and cannot be completely eliminated. It forms part of the natural background in any wireless system. Noise is random and does not carry useful information. Instead, it adds unwanted energy to the received signal, which can make it harder for the receiver to correctly interpret the transmitted data. There are three basic types of noise. Thermal noise is generated by the natural movement of electrons in all electronic components and conductors, creates tiny fluctuations in voltage and current, even when no signal is being transmitted. Environmental noise includes naturally occurring radio emissions from sources such as the sun, lightning, and other atmospheric activity. Man-made noise is generated by electrical equipment such as power lines, switching power supplies, and other electronic devices. Signal-to-noise ratio, SNR, describes how strong the desired radio signal is compared to the background noise in the same frequency range. It indicates how clearly a receiver can detect and decode a specific signal. In every RF system, there is a noise floor, which is the natural background level of noise present in the environment and inside the receiver itself. This noise floor sets the minimum signal level required for reliable communication. If the signal is only slightly above the noise floor, it becomes difficult to distinguish it from the background noise. A high SNR means the signal is well above the noise floor, resulting in better performance, higher data rates, and fewer errors. A low SNR means the signal is close to the noise floor, which can lead to reduced throughput, retransmissions, or dropped connections. Senior measures how clearly a signal stands out from the background noise, and the noise floor represents the baseline level of that background noise. Interference occurs when unwanted radio signals from other transmitters disrupt the desired signal. Unlike noise, which is random background energy, interference usually comes from other active devices operating on the same or nearby frequencies. When signals overlap, the receiver has difficulty separating the intended signal from the interfering ones. This can lead to lower data speeds, increased errors, or dropped connections. For example, when a microwave oven is in use, it can emit electromagnetic energy around 2.4 GHz. Although it is not intended for communication, some of this energy can leak outside the oven and raise the noise level in the surrounding area. This can interfere with nearby Wi-Fi signals, causing slower speeds, increased packet loss, or temporary connection drops. In short, interference is competing radio energy that reduces signal quality and network performance. PIM is a type of interference that can occur in radio systems when strong signals, often two signals at plus 30 dBm, plus 1 watt, pass through metal components that are not perfectly clean, tight, or properly manufactured. Even though the components are called passive, meaning they do not actively transmit or amplify signals, they can still create unwanted signals if there are small imperfections. These imperfections can act like tiny non-linear contact points that mix radio signals together and generate new, unwanted frequencies. PIM is a complex phenomenon, but a simple way to understand it is this: when two strong radio signals pass through a loose connector or poorly tightened metal component, the imperfect surface behaves in a non-linear way. Instead of passing the signals cleanly, it causes them to mix together. This mixing creates new unwanted signals at different frequencies that were never transmitted by the radio system. If these unwanted signals fall into a receive band, they act as interference and can reduce network performance. QPSK is a digital modulation technique. All modern RF standards use adaptive modulation such as QAM and QPSK, meaning the system automatically selects the modulation scheme based on signal quality, senior. QAM and QPSK is applied in both 4G per LTE, 5G per NR, and Wi-Fi. Modern networks dynamically selects the modulation scheme based on current signal conditions. When signal quality is good, higher-order modulation schemes such as 16 QAM up to 4096 QAM are used to achieve higher data rates. When signal strength is weak or interference and noise levels are high, the system switches to QPSK because it is more robust and less sensitive to errors. QPSK is therefore commonly used at the edge of a cell, indoors where signals are weaker, or in environments with significant interference. It provides a balance between data rate and reliability. Trellis coding tolerates poor signal quality. Trellis coding improves reliability by adding error protection to the transmitted signal, allowing the receiver to detect and correct errors. It does not improve signal strength or SNR and remains dependent on signal quality. However, it increases robustness and helps sustain higher-order modulation, from 16 QAM up to 1024 QAM, under challenging conditions. Modulation versus throughput versus signal level. In both 4G LTE and 5G NR, throughput is determined by signal quality and the modulation scheme in use. Better signal conditions allow for higher-order modulation, leading to increased data rates. While wider bandwidths and advanced technologies such as MIMO and massive MIMO enable higher speeds, they also require strong signal quality to achieve their full potential. In the diagram below, we have summarized the relationship between signal strength, signal quality, and modulation. This helps illustrate how these factors are interconnected and how they influence each other. Understanding this relationship is key to achieving optimal performance in both 4G and 5G connections. In this mini-course, we have built a clear understanding of the most important signal metrics and how they affect wireless performance. We learned that RSSI measures the strength of the received signal, but it does not tell us how clear or usable that signal actually is. A strong signal alone does not guarantee good performance if it is affected by disturbances. We also learned that signal quality reflects how much the signal is influenced by noise and interference, and that it is this quality that directly impacts user experience. Noise is the natural background RF energy present in all systems, while interference comes from unwanted signals that disrupt communication and can cause transmission errors. In addition, we discussed PIM as a hardware-related form of interference generated by metal components that unintentionally create unwanted signals. Finally, we reviewed how modulation and coding techniques such as QAM, QPSK, and trellis coding improve reliability by correcting transmission errors. However, these techniques do not increase signal strength or remove interference, they simply make the system more robust under challenging conditions. Overall, this course has given us a practical understanding of how signal strength, signal quality, interference, and error correction together determine real-world wireless performance. Before you go, don't miss what's coming next. At Weisenfeld Tech, we are building a growing library of high-quality technical micro-courses, delivered through modern e-learning. The courses are free, short, practical, and designed to create real value. On our YouTube channel, we will continue to explore many smaller technical topics. Areas that both beginners and experienced technicians often find interesting and useful from a technical perspective. By subscribing, you'll get access to new content as soon as it's released and be the first to discover upcoming micro-courses. Subscribe to our YouTube channel today and explore more at www.weisenfeldtech.com. We look forward to continuing the learning journey with you.